Couple more functions left in the catalog to find the derivative of. So as far as logarithmic functions go, just recall that ln of x, the natural log of x, is the inverse function of e to the x. So it's the inverse of the exponential function. We can't find this thing's derivative directly, as in using the definition, but we're going to use some tricks we've picked up to figure it out using implicit differentiation, and we're specifically going to use the fact that we know that the derivative of e to the x is e to the x, and we know that the chain rule works, and this is one of the things we can do with implicit differentiation. So this is going to be a little mathy, but here we go. So the natural log is just shorthand for a log base of e. It's just a special log base that gets its own name. So we're going to say y is ln of x, and we want to find the derivative of y. We want to find y prime, or dy dx. So we rearrange that using the definition of inverses. That's not calculus. That's just literally what inverses are. If y equals ln of x, then x is e to the y. If that doesn't make sense to you, then refresh yourself on inverses. We know that we're allowed to differentiate both sides of that equation with respect to x. So this is implicit differentiation. So the derivative of e to the y equals the derivative of x. The derivative of x is just 1, and the derivative of e to the y involves the chain rule. So this is e to a function. So the derivative of e to a function is e to the function times whatever the derivative of the function is, which, if you recall, is the whole thing we're trying to figure out. So e to the y times y prime equals 1. Solve that guy for y prime by just dividing both sides by e to the y. So y prime is 1 over e to the y, and then here's always the part of like the math proof trick where you put things back the way they found it. So we say, wait, what is e to the y? What was that in the first place? Well, if you go all the way back up 4 lines there, e to the y is x. That's how we defined it. So y prime is just 1 over x. If that seems too simple to be true, it's just one of those cool things. So that's it. That's the derivative of the natural log. The derivative of the natural log of x is just 1 over x. So this is the first time we've really seen a function where the derivative of the function is not even the same kind of function. The derivative of logarithms are just like rational functions like this. They're not other logarithms. And it's also the first time you're going to see where when you take the derivative of a function like this, it kind of gets simpler. Most things get more complicated when you start taking derivatives. But natural logs is just one of those things that's just how it works out. The derivative of the natural log of a number is just 1 over that number. So, like if you're there at 3, the slope of the tangent line at the natural log of 3 is just 1/3. If you're at 4, it's just 1/4. If you're at 5, it's just 1/5. I hope you like my GIF. So when we play around with this with the chain rule, some kind of unique things start to happen. So we're just going to do examples using this in conjunction with the chain rule. So the derivative of natural log of 5x is just going to be 1 over 5x times the derivative of 5x. The derivative of 5x is 5. And 1 over 5x times 5, those 5's cancel out. And somehow the derivative of ln of kx is still just 1 over x. Nothing changed. It's still exactly the same derivative. So you see what I mean? It gets simpler. If you have the natural log of x squared, now if you remember how powers inside of logarithms work, this might make this make sense more. But if you just use the chain rule, it just does its thing. So it's 1 over x squared times the derivative of x squared, which is 1 over x squared times 2x. And there's nothing wrong with canceling out one of those x's. So we just get 2 over x. So it's essentially the same thing, just with a 2 in there. Here's a weird one. The natural log of secant of x, so same deal. Chain rule says that's 1 over secant of x times the derivative of secant of x. The derivative of secant, recall, is itself times tangent, so it's 1 over secant times tangent, which wouldn't you know? You can cancel out that secant, and that simplifies to just tangent. So you see what I mean? It got simpler. But this is also, make a mental note of this, this is the first time we've seen a function whose derivative is tangent. So if you think back to those 6 trig derivatives, none of them had a derivative who was just straight up tangent. This is a function whose derivative is tangent. So this is something we would call an antiderivative for the tangent function. That's going to come up later. Yes, we have to do derivatives backwards. And if you need a backwards derivative for tangent, this is it. It's natural log of secant. Don't worry about that for now. Just worry about how the chain rule works with the natural log. We're going to basically do the same work we did on the natural log, except for other log bases. And it's going to work out almost exactly the same, only it's going to be like it was for exponential functions, where if the base isn't e, then something else pops up. So same deal. If y is the log base b of x, then by definition b to the y equals x. That's not calculus. That's just literally the definition of what a logarithm is. And if that looks unfamiliar to you, then refresh yourself on how logarithms work. Differentiate both sides. Right-hand side is just 1. And now think back from the exponential stuff. The derivative of b to the y is the natural log of b times b to the y times whatever the derivative of y is. All right, so the base is just some number. Just imagine the base is 2. So it'd be like the natural log of 2 times 2 to the y times whatever the derivative of y is, which is just y prime. That's the thing we're trying to figure out. Divide both sides by natural log of b times b to the y to get y prime by itself. So it's y prime is 1 over the ln of b times b to the y. And then again, put it back. What is b to the y in the first place? Oh, that's x. That's the way we defined it. So it's just 1 over the natural log of the base times x. And that's the derivative of any other logarithm besides the natural logarithm. People have a hard time remembering this one. So if you ever have to memorize this, the way I think about it is that if the base were e, then the natural log of e is just 1 by definition. So that's actually the same rule. So the rule for natural logs, which is easy to remember, is just a specific instance of this rule where the natural log of the base doesn't show up because it happens to be 1. Right, so all logarithms have the same rule. Just in the case of the natural logarithm, which is a special one, the ln of b doesn't show up. Just let's do some examples of this kind of stuff. So just the other log base on your calculator is the log base 10. That's the one you used before in algebra class when you crunched these, figured these things out. So it's the same kind of thing. It's just 1 over x. There's just a natural log of 10 thrown in there as well. So that's exactly it. It's just remember, natural log of 10 is just a constant, so it's just a stretched version of 1 over x. That's about 2.3, right? So that's still just a rational function involving x. It's just 1 over about 2.3 times x instead of just 1 over x. Okay, let's get a little more hardcore here. The derivative of the log base 2 of x times e to the x. So chain rule here, because we have the log of a function, except that inner function is also a product. So when we do the derivative of the inner function, we're going to have to use the product rule. So first we deal with the logarithm, because that's the outer thing. So it's 1 over the natural log of 2 times the inner function, times whatever the derivative of the inner function is. The inner function is x e to the x. So you should almost be able to do the product rule in your head here. It's the first times the derivative of the second, which is just x times e to the x, because e to the x is its own derivative, plus the derivative of the first times the second, but the derivative of x is just 1. So the derivative of x e to the x is x e to the x plus e to the x. That's a mouthful, but that's what it is. That's what it shakes out to. So you could leave it like this, but as we're kind of seeing with logarithms, these strangely do simplify. So if you just put that over that, you'll see that every single term has an e to the x in it. And there's really nothing wrong with then canceling it out. When you cancel it out, you get x plus 1 over natural log of 2 times x. So you see what I mean? It's just, we started with a function that was nasty. It was a logarithm of a product of x and an exponential. And its derivative turns out to be just a plain old rational function. If you were to graph this, it just is going to kind of look like 1 over x. The log base 5 of tangent squared of x. So this is going to be a couple applications of the chain rule. We have 3 nested functions here. The fact that the log base is 5 doesn't really change anything. There's just going to be a natural log of 5 in our answer somewhere. It behaves just like any other log base. So we deal with that first. It's 1 over the natural log of the base times whatever the inner function is, and then times the derivative of the inner function. So now the next function in is not the tangent, it's the squared, right? Because it's really tangent of x squared. So first we deal with the squared. So it's times 2 times tangent of x times the derivative of tangent, right? The derivative of a function squared is 2 times the function times its derivative. The derivative of tangent is secant squared. And we're done. We could leave the answer like this. To me, it's crying out to be simplified just because there's a tangent x in the numerator and a tangent squared of x in the denominator. So there's no reason not to factor out one of those tangents. 2 times the secant squared of x over the natural log of 5 times the tangent of x. That's as good as we're going to get it.